Good afternoon, ladies and gentlemen. Uh, yeah, it's nice to see you here, and I feel like from a different world from the tunneling. My speech is about the Prague City Ring Road. It means that this is nothing about underground repository, nothing about nuclear waste, but I hope that I will find some intersections, some shared uh, connections or recommendations. So, at the beginning, some basic data. We are a small country in the heart of Europe with a population about 10.5 million inhabitants, and actually, we hold the presidency of the Council of the Europe Union. Something about the transport. There are about 56,000 kilometers of roads and motorways, and about 1.3 thousand kilometers of motorways in operation. The Prague, the capital of the Czech Republic, has about 1.3 million inhabitants, and it is a famous historical country, and I'm sure that some of you visited it in past. Something about transport. There are 4,000 kilometers, 32 bridges over the river, 11 tunnels. And what is very important is a division of transport work where about 37% made up of public transport. It is very, very important. Here we can see just short information about transport. We have got the 3 metro lines, 35 tram lines, and 170 bus lines. And here on the right, here we can see a division of share of transported passengers in Prague last year, and you can see that metro, tram, and bus has the same amount of 1/3 approximately. So this is just a basic information about public transport. And here on the left, we can see a transport performance in a million vehicle kilometers. And this graph is interesting, especially here, because you can see the change or growth in 1989 when the political system has changed, and you can see the growth of transport performance after that. On the right, you can see number of passenger car owners of cars per 1,000 inhabitants. So as you can see, car own almost everybody on average. And here is just a short information about financing of transport. And in a first step, we can see revenues and expenditures from Prague during last years, and we can see that is something less 4 billion euro. And the tab which is below shows what are expenditures on transport, and it is about 1 billion euro per year. What is very bad is that unfortunately all expenditures are paid by Prague without any contribution from the state budget. It's really bad. All politicians are talking about it, and I hope it will change because it's 1 billion euro. It's too much money. And now about main communication network. It is formed by 2 rings, inner and outer, and 7 radial roads. Red color represents parts which are in operation now. And I would like to talk about the following 2 construction, about the Blanka Tunnel complex and the remaining part of the city ring road. So the Blanka Tunnel complex has a total length about 12.6 kilometers, and it contains about 11 kilometers of tunnels in a town. It is about 87% of total length. It was constructed since 2007 to 2015, and total cost was 1.7 billion euro. This project use 100,000 vehicles per day. The whole project is divided in 3 tunnels, and it contains 4 technological centers and 2 underground garages. It underpasses an urban conservation area registered on the UNESCO list and natural monument and Vltava river. And this project was designed, implemented, and successfully operated the very sophisticated fire ventilation system. Here we can see transport tunnels, ventilation machinery room, and ventilation tunnels. Red and orange color represents exhausted air, and blue color represents fresh air to the tunnel. Every about 80 meters, there are the special openings which are connected with the ventilation corridor which is under the road, and this corridor is connected here to the ventilation machinery room. So it means that in case of fire, the smoke is sucked to the corridor, to the ventilation room, and outside of the tunnel. At this video, you can, I think, see very clearly how it works, because this is the smoke detection test. So you can see it. It's the most useful to try it exactly. And now you can see how the ventilation is working, how the opening is able to suck it, and it allow to escape to people in case of fire and so on. So it's very, very useful. Yeah. Of course, it is a very complicated construction. Some parts are very, very complicated geometrically, and it was necessary to use the finite element method in 3 models for this project. And the excavated ventilation machinery room, as I mentioned before, is one of the largest underground works in the Czech Republic. It has 20 meters in diameter and about 300 square meters across section. And you compare the picture on the right to building which has about 5 floors. So the Blanka tunnel is really equipped a lot, as we can see from the safety point of view, according to the standards. It's not necessary because of time to explain everything. I think it's clear. But from a technological point of view, it contains, of course, tunnel lighting, camera system. This system allow automatically detect smoke, slow car, passengers or people on the road, and so on. And of course, pollution concentration measurement. Vehicle speed measurement, it's really necessary, because to keep maximum speed is necessary in the tunnel. Fans, warning and information signs, emergency lighting of pavements, and variable information boards and road markings, and linear fire detection. Yeah. This tunnel is controlled by a sophisticated control system under the supervision of police and technology dispatcher. At the picture, we can see the traffic management center, how it looks now, and here we can see the new one, which is under construction now and will be put into operation in 2023. So I think this is the first intersection to underground repository, the construction, which is fully equipped by technology and is controlled by a sophisticated control system. I think it is very, very similar. Yeah, it's very complicated to build a construction in an urban area. It's the construction is a short time nuisance for people for local people who living around the construction. So for this reason, the special information center and or visitor center and a special website were established. So I think this is the second intersection, and it is necessary very intensively communicate the construction, everything about it to the people. So it's, in my opinion, it's very, very important. And for this reason, this information center and website were established. The Blanca tunnel, it's not only tunnel for vehicles, it's a new park, it's new tram stops or reconstruction of tramways or a new bridge, which is, in my opinion, a new architectural landmark of the city, especially in the night, as you can see here in these pictures. So this is other intersection, I think, because the construction is not just about this project, but it is about benefits for people who live around it, who are interested in this project. So it's necessary to make some benefits with this project, not only focus on, for example, in this case, vehicles and a road for vehicles. Yeah, yesterday it was 7 years when the tunnel was put into operation, and in my opinion, it was a really big day for people who are living in Prague. Impacts. What impacts we had? It's completely, I think, clear at this picture, because it is the picture of the same street before tunnel and after tunnel. So it means that we rapidly decreased amount of cars on the surface. And of course, not everywhere. There are some places that it is not so good, especially at the end of the Blanca tunnel complex, where the remaining part of city ring is missing. So it is a complication, but we are trying to do it as good as possible. So very carefully we monitored traffic and environmental impacts of the project, and we in detail to publish on website, in metro and on billboards. It's I think again very similar like in case of underground repository. It's necessary to do positive public perception, and it is very important in our case for the further continuation of construction of the City Ring Road. So it means that it's necessary to give the positive information from existing project and to give it to the people, to inform them about it, because it's more easier to plan and discuss new construction. Yeah, I think this is other intersection. Just a few sentences about the cost. As I mentioned, the total cost was 1.7 billion euro, and it was about 30% higher than it was expected at the beginning. What were reasons? As a first, it was unexpected geological conditions. It was about 17% from 30, but it is the same, of course, like in underground repository, but not exactly, because at this case the tunnel underpasses really bad and complicated geological conditions, but as I understand, geological underground repository, we designed the best rock conditions as is possible. So it could, but the problem it could be as well, and about 5 or 7, I don't know exactly now, percent, it was new client requirements. So after the contract, a client decided to do a larger scale of reconstruction of roads, parks, and so on, and it of course increased the price. And the other reasons were adjustment or new technical standards which client decided to use. And as I mentioned, the construction started in 2007 and finished at 2015. So again, intersection compared to underground repository, it's a question of money and the risk during underground construction. If this is underground construction, and it is very necessary to think about the system of contract, if to use yellow FIDIC, red FIDIC, emerald FIDIC, and so on. And it is everything has advantage or not, and it's necessary to very intensively communicate it and to choose the right solution. Yeah. Now about the remaining part of the city ring road, again, basic data. The total length, it has about 21 kilometers. From EA documentation, the total amount of tunnels was about 10 kilometers, and it was 57%. And in documentation for a zoning decision, now it is something less 17 kilometers. It is about 80%. So it has changed a lot from 57 to 80%. We plan construction time. The construction will start about 2028. And actually expected total cost is 4.5 billion euro. And as it's clear, this part of the city ring road. Yeah. Now I would like to talk about the societally acceptable urban design and minimalization of environmental impacts. Here we can see the global layout from EA documentation, and with dotted line, I hope I think it is visible. Dotted line represents tunnels and full line above ground roads. Other global layout, it's a little bit different, is from documentation for zoning decision. And with the yellow, I hope it is, with the yellow color you can see tunnels, so it is 80%. It is almost in tunnels except this part. At the end, where are not any buildings located and so on, and there is designed above ground road. And now we will see some visual comparisons between how it looks now, how it was designed in EA documentation in 2010, like here, and now what is final technical solution in documentation for zoning decision. So in this case, you can see how it looks now, and this technical solution you can see here of city circle, and it's a above ground road which follows the river here, and in actually it has been completely changed, and you can see the portal of the tunnel, and the city ring road is on the surface with the whole length here, and this road it is the same like here existing road, so it is this one is just for pedestrians, cyclists, and so on. So it's very nice to walk around the river and so on. I forgot to say that on the right you can see the place where the visualization is located. Other example, again, how it looks now in 2022. What was a solution from EA? And you can see again the city circle as a above ground road between buildings. The new solution now is here again. There is a city ring road, but underground there is nothing above ground, just tunnels, and it allow, for example, or will allow to build up this area, new buildings, or to plant new trees and greenery generally, and so on. Other example this from other side again, how it looks now. What was the solution of EA, and you can see again the city ring road as a above ground road here, and technical design from DZD, where the tunnel, where the city ring road is again like a tunnel, and here we can see just roads for local transport with low intensity of traffic. Next visualization is from this part of the project. Again, how it looks now, the previous technical solution from EA and new technical design from DZD. As you can see again, less roads on the surface and more greenery. Last example of visual comparisons is from the end of the project. You can see that there are not so many changes here because this area is not full of buildings, and generally there are not planned new buildings here. So this part is above ground. So at previous slides, I would like to show you that it's necessary to design the construction very carefully to minimize environmental impacts, and again to try to put construction under the surface. And it is the same, in my opinion. It is like in an underground repository. It's clear underground repository is underground, but the part at the surface, it's like a factory. It's necessary to think about it and to offer some benefits and try to, in my opinion, to hide it underground as much it is possible. And the last part of my presentation are some experience from already operating sections, and it's focus on transport tunnels exactly. This is an example of GPS signal. You can see it's very useful to have a GPS signal in the tunnel, because especially, and of course, in tunnels with intersections inside and with crossings, it is very, very useful, because especially at the portal, without GPS signal in tunnel, the navigation can start to work and can advise to driver turn the right, and he's trying to the right in this case, and it is it's risky. It's the risk of accident, and it's necessary to minimize it. So it is very, very useful to use a GPS signal. The other example of experiences is a minimizing on traffic regulations of the tunnel. So in this case, the tunnel is divided into individual smoke sections, and it allow to close just a necessary part of the tunnel, and other part or remaining part can be in operation. So it's great. Of course, it is again about tunnels with crossings or intersections inside, because what is effect if you close the tunnel? All vehicles have to go outside on the surface, and the traffic jam is terrible. So it's necessary to minimize it. Again, I have to say that I am talking about tunnels with intersection. Tunnel from A to B without any crossings and possibility to get out is it's quite different case. And other example is, I think, important as well. It is necessary to think about alternative roads. It's connected with my previous slide. If I open the tunnel and I rapidly decrease amount of cars on the surface, I can change it. I can plant new trees. I can make new park or cycle lanes, and completely change it, because there is a really small amount of transport or traffic. But in a case of a fire or an accident, when I have to close the tunnel, all cars are have to use surface road. But in this case, previous or former road on the surface is missing, so it is terrible. And the solution is, for example, to use or to create bus lanes and to use varying road signs. And when the tunnel is operated, it's just plain for buses. And then in the moment when I need to close the tunnel, I can change the road sign, and the lane is able to use for all cars. So it's necessary to think about it. And it is together, I think, connected again with the repository. This is the last example, because the competition of the ring road allows the introduction of more restrictive measures for entering the central part of the city. So and it allow to use, for example, toll around, and to really to do something, not to use cars in the center, but it is really very complicated politician decision to use a toll in the center of Prague. And we will see how it will continue. Yeah, now we are at the end of my presentation. I will not read it exactly, but I think that I found some intersections where you can have some share problems, like in underground repository, and some of them are that it's necessary to communicate it, to be aware of money, and to look for the right system of contract, which is very, very, very important. Yeah, that's all. Thank you for your attention.
The outline of the presentation, there's 4 parts to it. I'm going to describe the context to it. I'm going to describe the approach to optimization on decommissioning in end states. Then I'm going to provide a worked example at Traus. We shorten it because the pronunciation is difficult. We generally just say Traus when we're talking about it. And finally, I'll give you some conclusions and try and summarize the relevance to geological disposal optimization. And first of all, just a big thank you to the colleagues that have been working on this, both colleagues at Magnox and in the company, Golson Sciences. This has been work actually that's been developing over quite a few years now. And the motivation behind it is summarized here. The UK Nuclear Decommissioning Authority has been around for a little while now. They own 17 nuclear sites, including all their assets and liabilities, 11 of which are Magnox reactor sites, and a few others are actually Magnox-owned research sites. The important background is this document here that was published a few years ago by the UK Environment Agencies. And what this guidance gives is a new approach to thinking about decommissioning in end states for nuclear sites. And it's guidance on how to release a site from regulation. This was a very helpful initiative by the regulators. And what they're really wanting the industry to do, decommissioners, is not to think of off-site disposal of decommissioning waste as the only option for a decommissioning strategy, but to think about alternative, potentially on-site options for disposal, particularly for high-volume, low-activity decommissioning waste. And what this slide shows, and this set of pictures is actually a set of pictures from the regulatory guidance itself. What the environmental regulators want you to think about are options, a range of options for on-site disposal of radioactive wastes from high-volume, low-activity radioactive wastes from decommissioning. And what's the rationale for this? Well, basically it comes from a consideration of the detriments associated with off-site disposal, off-site transport and disposal. And when you think about it, there are safety issues, both increased sort of detriments to worker safety, both radiological and non-radiological. There's large environmental nuisances, a larger carbon footprint. There's cost, both of the decommissioning operations, but also the off-site disposal costs. And certainly in the UK, and probably not only in the UK, engineered disposal at national sites is a scarce resource and needs to be properly managed. And if we can find other solutions, then it behooves us to think about them. So there's a range of detriments that are that need to be thought about, and long-term radiological safety is not the only issue in this decision, but of course it is an important issue. So the central propositions for making progress on this is, first of all, to think about the question, for a particular nuclear site, is it possible to think about the disposal on site of these sorts of high volume, low activity, radioactive structures, or indeed even potentially contaminated land? And what are the implications of thinking about that in terms of optimization compared to a clean site, digging up all the material and sending it somewhere else? And the way to achieve this was to come up with the concept of a starting case end state. This is the final end state that you leave the site in when you want to be able to release it from regulatory control, as a starting point for optimization and for a purpose of comparing with the clean end state option. And what I've summarized here are the attributes, what we would regard as positive attributes of a good starting case end state, or if you like, a base case, it might be called. And the attributes are systematic, transparent, comprehensive, and being as simple as possible. And why those attributes? Well, the main importance of things like transparency and simplicity is that this is a major change in strategy, no doubt. And in order to implement a major change in strategy, you've got to bring stakeholders along with you. Stakeholders will include, first, internal decision makers within MAGNOX, within the NDA. They will include local stakeholders who would have to agree to this sort of revised end state. And of course, there's regulators as well that have to be convinced it's the right option. They've set guidance to think about, but they haven't made the decision. The decision has to be made by the decommissioner, and it has to be made on a local level. So those are positive. Those are the attributes we're looking for as a starting point. And the way this has been defined by MAGNOX is, first of all, what can we do to minimize off-site transport of materials? And by minimizing that, what they're actually looking at is minimizing the quantity, not the activity, but because clearly all of the higher activity materials will need to be taken off-site. So this is very much focused on low activity, high volume wastes. And what might the credible candidates be for leaving structures or materials on site at the final end state of a decommissioning program? So the starting case end state is, of course, not the preferred end state. It's only a starting point for optimization discussions. So that's an important aspect. And along with that is the concept of iteration. It won't be a one-pass process. It will be repeated as the program advances, and this is foreseen in the regulatory guidance as well, because there are actually two requirements pertaining to optimization in it. First of all, there's the decision of whether or not it even makes sense, whether it's optimal, an optimized solution to leave any material on site at the final end state. And certainly radiological assessments are part of that decision. They will inform the decision on it, but they're not likely to be the determining factor because of the other issues I mentioned, the other detriments associated with off-site solutions. So that's one thing. And the approach to doing this is to come up with an end state that's essentially has no mitigations in it, and then to examine potential ways to improve that end state through mitigation. And this is the second part of the staged or graded approach in the regulation, that once you've reached a decision that yes, some material could be left in principle on site, the next step is, what's the best way to do it? How do we optimize that solution? So I would call this a graded approach to optimization, whereby you make a decision first on the higher level question. You define that as simply as you can, and then you might have a lot more detail that comes into the lower level decisions, and they might need a lot less stakeholder input as well at that point, once the primary decision is made. This methodology was subject to dialogue with regulators and also peer reviewers. And it's kind of well internalized and being rolled out now across Magnox sites. The site that is at the front end of this, and I'm going to talk about this now, is the Trouse site in Wales. And the site had up until this site is being, if you like, is the lead site for applying this approach, because it's in a national park. So it's in a scenically important area. It was one of the sites that's been prioritized. The original option, as for other sites, was to have an end state around 2080 with no remaining radioactivity on site, so a clean end state. And now the approach that's being implemented is to look at these features, the high volume, low activity features that might be left behind, and the structures that are most important to think about. The typical structures are reactor bioshields, cooling pond structures. These cooling ponds are essentially where spent fuel was cooled prior to sending off to the Sellafield site for reprocessing. And indeed, on this site and other sites, there's areas of contaminated land that need to be considered. This is broadly, I'm sorry for not having a better picture, John, but this is broadly what the site looks like today. There are two reactor blocks. You can see the ponds complex in front of them. It has a pretty large extent, actually. It's a large structure in its own right. The turbine hole is now long ago demolished, and there's an interim store on the site for intermediate level waste. The spent fuel's all gone at this point because the reactor shut down quite a long time ago. This slide is there simply to show you, to illustrate the extent of the underground voids available. So part of the strategy is, if you're going to leave material on site, radioactively contaminated material on site at final end state, can you make use of pre-existing openings that are already there below ground? And the main ones on this site, and indeed on some other sites, are the cooling pond structures and the reactor voids. So this is just to give you an idea for the void spaces available. And this is to give you a better idea about the scale. This shows the reactors during construction. The important point is that the reactor bioshield is a very thick concrete structure, about 3 meters thick. There's a lot of material, about 1 meter of which is contaminated at this point. There's a base slab at the bottom of the construction. That is at a depth of about 4.5 meters. So it gives you an idea about the extent of the underground void space that's available on the site below the reactors. So in order to define the starting case end state in terms of inventory at Trouse, first of all, obviously, a number of kinds of wastes could immediately be excluded. So the reactor core graphite is still on the site. That doesn't fall within the scope of this study. That has to be disposed of in another way. There's also some non-radiological hazardous components, asbestos in particular, quite large quantities that wouldn't be candidates, and readily removable metallic components wouldn't be candidates. So the focus very much is on the large volume, low activity structures and the contaminated subsurface ground. So the one thing is to define the actual structures under consideration, and the second thing is to define a geometry that needs to be thought about. And this basically is what the site, in terms of these major structures, looks like today. So there's the reactor envelope plus the bioshield inside it, the yellow structure on the left-hand side, and you can see radioactive contaminated ground, leaks from the ponds of unknown extent, and then a possible end state, a hypothetical starting case end state configuration on the right-hand side that might be there, that's assumed to be there at the final end state. And so the first assessment is just looking at it like that. The above ground material is collapsed into the void space, and there's 1 meter of clean cover, and that's it. So if that's the first test. Is that good enough just to leave it like that? So the starting point is an end state defined like that. So no substantial mitigations. And then that is used for 2 purposes. First of all, as I mentioned, to inform the strategic decision already made, in fact, a couple of years ago, about whether or not any radioactivity should be left on site. And to provide a base case with comparison with variant end states that might incorporate 1 or more feasible mitigation measures. The performance measures, the radiological performance measures used for these assessments were essentially long-term performance assessments considering human intrusion and groundwater pathways, and looking at for groundwater assessments, a risk-based performance measure in the guidance, for human intrusion, a dose-based measure. So in terms of the optimization aspect, one thing that was important, that we found to be important, is in order to define realistic engineering mitigations, it was important that the assessments themselves were realistic, because overcautious assessments could well lead to non-optimal mitigations. Here is a list of potential mitigations that were looked at. They were essentially targeted reduction of particular features or removal of radioactivity, conditioning of waste, so how you actually collapse the above ground structures into the voids, looking at mitigations to do with fast pathways like contaminated drains, and radioactive decay. Those are all optimization measures. And then you could come up with a table that looks like this. So you see there the different key features I mentioned, the pathways, radiological pathways that I mentioned, the potential mitigations, and then the radiological impact. So what did we get with the starting case? And then with the mitigation, was there improvement or not? What was the magnitude of the cost? And a decision that could be taken on whether to implement the mitigation. And clearly, where it's red, the mitigation is essential. Where you're just changing the color of the green, that actually is an optimization measure. So this is just to summarize the methodology that's being used, has been used. And what I want to do is make some summary statements now. So first of all, I again would stress that the features of a starting case end state for optimization, these were major decisions that are being made to completely change the final end state of reactor sites. And the requirements of that were to have a methodology, a tool, to bring stakeholders along with this major change. And the features that have been described here, basically a system, a methodology that could be rolled out across all magnox sites in a systematic way and consistent with the guidance, clear criteria on how to use it, and comprehensive in the sense that it would allow consideration of a wide range of potential mitigations. And finally, a need to avoid using complex options, at least for the initial site-wide assessment. And finally, just to Lessons for optimization of geological disposal. Clearly, optimization has an important role to play in change management decisions, as has been mentioned by other speakers, in a very long-running project. Both decommissioning and disposal projects are long-running. And we used optimization as part of the tool, one of the tools to bring stakeholders along with some changes to strategy and also the way to implement the strategy once it was agreed. So I've already mentioned about the importance of a clear starting point or base case, a clear description of that. Early stakeholder and regulatory engagement was really important, both for agreeing the methodology to be used and rolled out, and also on the details of the assessment approach. So both aspects were important. The staging was important, the method to have agreement on a high-level decision at a fairly simple level before very detailed engineering mitigations and assessments and options were laid out at the next stage of the assessment. It's quite important that all the options considered have the same endpoint. So for a geological disposal program, you wouldn't make sense to compare end state a disposal option with a long-term storage option because that isn't the same endpoint, but it would make sense to consider various kinds of disposal concept at a particular site. And the balancing of decision attributes was challenging. It can be challenging. And one of the lessons is, though, of course, that you need to focus on those attributes which make the greatest impact on the decision. In order to get to that and for stakeholder buy-in, you actually need to show that you've considered all potential attributes and made the argument that some of them are less important, some of them are more important to the decision. Finally, there needs to be time allowed for iteration, and we need to consider, though a lot of disposal safety cases are based on conservative approaches in order to get approval to go ahead at a site. From the point of view of optimization, improving the design, those assessments need to be based on a much greater level of realism to ensure that we don't end up with non-optimal outcomes. So thank you very much for listening. And the final slide is just some acknowledgements to colleagues that were involved in the study and the independent peer review I mentioned.
I started my career always with major projects in water power construction, and later on I became responsible for the construction for the civil work of the Gotthard Base Tunnel. And this will be the basis of my presentation, because now I'm a little bit older and I was thinking about the success criteria and the success factors for these major projects. And I will talk to you a little bit from the upper level. I don't want to go too much to the details, but if we take the title of this presentation, Success Criteria and Success Factors for the optimal planning, construction, and operation of large infrastructure systems, we have to ask what are characteristics of large infrastructure projects. Many of them we have already heard. But then what means optimal planning, construction, and operation, and what are the typical success criteria and success factors? And I would like to start with characteristics of major infrastructure projects. I think very characteristic for major infrastructure projects, as your projects also, is the high complexity. And this is related to a lot of interfaces with a lot of involved partners, and this makes it rather complex. Then this creates a high level of interdisciplinarity. It's not only civil works, you have a lot of for instance, on the left-hand side, hydropower plants, electromechanical equipment, and control systems. So it makes it very complex. And as we also have heard, we have normally very long project duration, which makes it very difficult to manage this these projects. I think the long duration is one of the main aspects of such projects. Then high investments, we have also heard, high public interest, and very often you have a certain level of uniqueness in those projects, and this leads often to innovative solutions. So the success factors for the project are the root causes for a sustainable, really sustainable success of the project. And if we take here as an example, a project, I want to go to this mountain, then I need success factors that I can reach this top of the mountain. I need to reach the right clothes, I need equipment, I need food and everything. And I have also to think what happens if the weather becomes bad or different than what I expected. So a project starts with the idea and with the listening or with creating a list of the requirements, and the goal is that the requirements are finally fulfilled. These are the success criteria. And as we all know, the way on the top, we have a lot of processes to fulfill, and these processes are subject of threats or chances of risks. And what we have to do is to define and implement measures that we can control the threats or that we seize the opportunities. These mitigation or these measures, these are the real success factors also that we can reach our goals. It's a simple slide here, but I think it's important the logic behind that we are aware about this. So the definitions of the success criteria, these are the predefined project requirements by which the project is judged at the end of the project, whether it is successful or not, and the success factors are the root causes, as I mentioned already, for the sustainable success, not one-day success of the project. It was also mentioned already before, but I'm coming from traffic projects during the last years. It's not everywhere accepted that one has to think always in the entire life cycle. But I think that's very important, that if we are talking about project success, then it's the success, the fulfillment of all project requirements over the entire life cycle of our projects, and not only that we fulfill the next step. Also, if we are talking about optimization, I can show you this about with the example of the Gotthard bias tunnel. It's very important that we think also in the life cycle, in maintenance cost, operation costs, and not only in the initial investments. So what are the requirements of the today infrastructure projects? Here, that's a picture of the valley of the canton Uri towards the Gotthard. You see the different infrastructures, electric line, high voltage lines, then the highway, the new Gotthard line from the railway and the rivers. And you have many projects, and normally we have this famous triangle of the project management that we need, or that we are discussing about agreed quality. It must be on time, and very often we try to construct it with minimum costs. But it's more complex because our projects, they are embedded in a physical environment here in the mountains. If you have to cross the Alps with a long tunnel or the longest tunnel of the world, you have ground risks, and you don't know it at the beginning what's happening. So one has to be aware that we are our projects are in an environment which is not 100% stable. This is the physical environment, but also the social environment. There we know that the changes can be even quicker, depending also on political systems. And we have to be aware with our projects how we deal with all these requirements from this environment. Therefore, it's very important that we define at the earliest stage of the project project requirements, the success criteria. Here is an example with 7 points. I think in your projects it will be a little bit different, and safety is maybe number one, but in traffic projects you have quality, functionality, including the operational safety, but then occupational health and safety, especially for underground construction, I will show it, must be on a top level. Also environment protection, the revitalization of flora and fauna, because we are affecting this, and the sustainable use of the atmosphere and hydrosphere. Opposite to the project in Prague, as an example, this requirement for the Alp Transit project, for the Gotthard-based tunnel, led us to the reuse of the excavated material. The longest tunnel of the world has no cubic meter of alluvial gravel. Everything is reused excavated material. And this, I think, these are the things which one has to define as early as possible in a project. Otherwise, if you are negotiating with a contractor, it's too late. Then acceptance by a public is very important. Processes, organization, time, and costs are for me at the end, because costs and financing is the result of all the other requirements we have to fulfill. And very often, if you are discussing with political instances, then it's only cost, and always costs. But we should discuss all the other requirements before we discuss the costs. That's my opinion, and also the experience of it. If we have such criteria, then we should also to be able to monitor or to measure them. And for instance, in Switzerland, we have no agreed system how we can compare the success of the various projects. And in a master thesis at the ETH, where I was during a few years, we created such a system for these key success criteria with a 7-point Likert scale, where we have also the possibility of an overachievement. And with this system, we compared 45 Swiss underground projects and 25 in Germany, but I'll be talk only about the Swiss projects. The gray line shows the target value, and we were a little bit below. If we look at the scale, if we have the value of 1, then is a minor deviation. It's not very severe. So we were rather close to the target values in many or practically in all of the requirements. We divided it in the phase from 1980 to 1998 and 1999 to 21. And there you can see that we had a better values in the last 20 years than before. Only one point we had a negative development, and this was in organization and processes. And if you talk to the people in Switzerland, contractors or engineers, they tell you it becomes so difficult to have decisions from the owner side. And this is now based on these 45 projects. One can see that this is really a problem, and that it was mentioned by you. The type of the contract and how we work together is very important. Also, for your projects, I think one has to, already in the initial phase, one has to be aware how we want to construct this project. That's and we made also the investigation what happens if we don't work very well together, if we have a confrontational project delivery, then you have a very big risk that you don't fulfill cost deadlines or the organization and processes. That seems quite logic. So what are the success factors? What can support that we can fulfill our criteria, as I have mentioned before? There are external factors, and I think one very important factor is the political environment. the second one is the early stakeholder involvement, as it was mentioned also here before. I think one made also certain experiences. If I remember, even Naga had experiences in this field 30 years ago. So it's very important, the early stakeholder involvement. Then there must be also the will for searching for compromises. Otherwise, you don't find solutions. And I think very important is also an early and stable financing. I will try to show this later on with the example of the Gotthard Base Tunnel. Then you have also internal success factors within your own project organization, and I think it starts with the respect for the task and for its environment. Very often people say, oh, what's this? But if you are looking at the jokes of Mr. What was his name, the mayor of Berlin, this airport, we do it easily. There it starts. If you don't have the respect for this, for your task, then it's rather difficult. So therefore, this is for me number one. And then we also don't speak too often about this, but I think it's very important that you have the right people in the right place at the right time. Otherwise, it becomes also difficult. And then you need a culture where these people are able to work together. You can have the best people, but if they are not able to work together, you will have no success. This is also very important, and I can show you. We have made very good experiences also with certain simple values, but they help to have success finally. But with the first 3 points, you don't have constructed anything. So I think it's also very important that you finally have also a careful project preparation and then the execution. All this together you need in the minimum. Now I would like to show you how this worked for the construction of the Gotthard Base Tunnel. I think it's well known, but on the left-hand side it shows very well how complex this system is. It's nearly comparable with your constructions. We have shafts, caverns, many different type of underground work which had to be created successfully. Let's have a look on the first success factor, the stable political environment. We are happy here in Switzerland that we have this direct democracy and we can measure whether we have success with the population. We have 3 different types of public votes: the mandatory referendum, optional referendum, and the federal popular initiative. And all these tools of our democracy were involved in the project of the Alptransit and the Gotthard Base Tunnel, because the decision to construct this major line through the Alps, the optional referendum was organized by the Green Party, and we had at that time a party called Autopartei, also the party of the car owners and the Green together. They collected a little bit more than 50,000 signatures, and then this vote had to take place. And with nearly 2/3 of the voters, this was won. And later on, the people took an initiative that which prohibited the increase of the road traffic capacity through the Alps. Everybody thought this will not be successful, but it was successful, and this was also a very big support for this railway project to construct this. And then I will show you this financing became difficult, and one could solve it only with a new tax system and a new funding system. And also this was part of mandatory referendums, and this was also accepted. Now the stakeholder involvement in the 1960s, the The topic of this project was to connect northern part of Switzerland, the German-speaking part, with the Italian-speaking part of Switzerland, and we have a federal organization. The cantons were involved in the decision-making process and in the optimization of the projects. Finally, the Gotthard Road Tunnel was constructed, and after opening of the Gotthard Road Tunnel, one saw that the railway infrastructure has to be improved because it was not competitive anymore against the road, and it created problems. But at that time, it was clear that the construction of a railway line through the Alps is no longer a national task. It is the integration of Switzerland in the new European high-speed network, and it's a task on the European level. And therefore, the conference of the deputy traffic ministers was created from Germany, Austria, Italy, and Switzerland, and they made the recommendation that one axis has to be created through Austria and the other one to Switzerland. The decision was taken, and since 1990, the construction was on progress, and then the people were affected in Switzerland. And then it was very important that we had excellent relations with the cantons, with the affected communities, but also with the environmental organizations. And this worked very well and gave a huge support to the project. Then the all-round willingness to find compromises. Here a picture from the Reus Plain in Uri once more, and on the northern side there should be a future extension of the Gotthard railway line with a new tunnel, and the people there were requiring an underground connection between these two tunnels because they didn't want the heavy freight trains in this narrow valley. And this process to find a solution took 8 years. And one has to be aware, if we say we want to find compromises, finding compromises needs time, and this has to be also considered in our schedules. Then the stable financing. At the beginning, the first public vote was that the future generations, they have the main use of this infrastructure. They should pay it to 75%. So 75% was repayable loans, and only 25% from public funding. And one saw this will not function, especially after the experiences with the Eurotunnel, and the system had to be switched completely. Now everything was paid by new taxes, and as I showed you, it was a part of these public votes. Then respect for the task on its own environment. One was talking to other projects. Eurotunnel created exchange of experiences as you have here, and I think it's very important that you have such platforms where you can exchange experiences. But one said also, before the first public vote, what do we have to do that this project doesn't become a disaster? And the owners, designers, and contractors were sitting together and were creating new elements in the contracts that we don't have big problems. And finally, we have to say it was successful. We had no court case with a major contractor. The right people on the right place. Character, willingness, skills were the topics we were asking for, and we were very lucky that we had 80% from the people in this project from Switzerland and the neighboring countries, and this helped also from the language that everybody understood the other, and this was, I think, it was very helpful. And then what I mentioned, the ethical values. We had a very simple 3V culture at Alptransit Gotthard. Be a shining example, Vorbild sein in German, the first V. The second one was taking responsibility, not shifting responsibility always to others. This Verantwortung übernehmen. And the third one was giving and receiving trust. I think this is also very important. Vertrauen geben, the third V, and we were very successful with this. Then I think it's very important that we have a clear preparation and execution of the project, and that we think to the end of the project, that we construct the topic was to construct a new railway and not to construct the longest tunnel of the world. This became it only during when it started operation, then it was very important. But during the whole process, it was always the new railway line, documented in an operational concept, in a maintenance concept, and in a safety concept. These were the basic documents at the earliest beginning. And it was asked in another presentation, how did you manage this? It was very easy in this case. The total investment of Alptransit, also including the Lötschberg axis, were 22 billion Swiss francs, and the handbook from the government was this small folder with around 100 pages. So with this, we were very successful. Then very important is also the risk management from the earliest beginning. Simple, but it has to be made on the site, and you need also careful preparation and execution of the projects, which led in our special case also to the development of new materials, because we had such special conditions. So I will come to the end. Since 2016, the Gotthard Base Tunnel is now under commercial operation. It has a very high availability. The quality, I think, is given. The annual maintenance costs and operation costs are 68 million Swiss francs. It's rather high, but when we made the decision and the optimization, the operation costs had a very low percentage in this system, and therefore the cheapest investments were built, and not the system with the lowest construction volume was constructed, and not this which is maybe for long term the best one. And if we have a look to this, what is our final result in this system, then we achieved it rather well, only occupational health and safety. We have a very strong measuring system. We had 9 deadly accidents there. We have to improve, still to improve very much in underground construction. So my final recommendations: avoid to ring up an architect and engineer syndrome, as Michael Latham called it in his famous report. If you start as an owner, you have to define the success criteria and the success factors, and your architects and engineers can help you, but you are responsible. Then define your own key success criteria at the earliest beginning of the project and monitor them, and cultivate the key success factors, and implement a professional project risk management at the earliest stage as possible. With this, I come to the end. Sorry, I was a little long, but thank you for your attention.